Swayam Prabha. Digital India. Educated India.
Okay, let's get started. Let's get started with this slide which shows the journey to the Navier-Stokes. We started with the Newton's second law of motion, applied the Reynolds transport theorem, and then got the integral form of the linear momentum balance, and then applied this integral linear momentum balance for a small control volume, obtained the differential form of the linear momentum balance. In that we completed the left hand side. On the right hand side we discussed the gravity force alone, and then we said to understand surface forces we will take a diversion to solid mechanics, and then we discussed this block where we discussed about stress vector, stress tensor, the relationship between them. Then we carried over all the concepts to fluids, and that is where we discussed these two blocks. In that first we discussed fluids at rest, discussed the hydrostatic stress, and then we said in the case of fluids there is a stress under stationary condition and rest condition. When it flows additional stresses are there. So we introduced total stress tensor as sum of contribution from pressure and contribution from viscous stresses. Now we are in a position to complete the linear momentum balance, which means that we are ready to include the surface force on the right hand side, and that is what we will do. Then we will understand what this block means. Okay. In terms of outline which we are looking at right now, we have discussed the total stress tensor for fluids, discussed the difference between solids and fluids, and then wrote down expression for the total stress in fluids. Now we are going to discuss these two bullets, namely completing the differential linear momentum balance, which means we are going to include the surface forces on the right hand side, also discuss a new problem which will arise, namely the closure problem. Now we have derived the left hand side and the gravity on the right hand side a few lectures ago. So just to revise, we will quickly run through those two slides again now. So these two are recall slides, there is nothing new here. Okay. So first we started with the integral momentum balance, and then we applied this integral momentum balance for this small control volume. Okay. So when I say small control volume, a control volume like this, of course very small, inside the domain, okay. And then we expressed the rate of change of momentum term, and then the second, this integral represents net rate of flow of momentum through the control surface out of the control volume, and we have written this for the x momentum. So these 6 terms represent the net rate of momentum, the convective momentum terms, okay. And we also discussed that the different terms arise from the mass flow in the different directions. So the first two terms are the x momentum associated with flow along the x direction, that is why we have rho vx and rho vx here, and then because it is x momentum, the second velocity component is vx. So this accounts for net rate of x momentum because of mass flow in the x direction. Similarly the y direction, and then similarly the z direction. On the right hand side we have sum of forces acting, okay. And we divided by delta x, delta y, delta z, and then got this expression, and then we shrink the control volume to a point because we are looking at, we want to derive expressions valid at every point, and these expressions are related for average values of density, velocity, etc. Once we shrink, they become point values or local values, and we get this differential equation or differential expression for the left hand side of the linear momentum balance. So, this we have discussed already. So, left hand side is ready with us. Now, on the right hand side we discuss only the body force. Right hand side are the sum of forces acting on the fluid, and they are body force and surface forces. We discussed the body force. We also discussed that the body force can have all the x, y, z components, and we wrote the expression for the body force and divided by delta x, delta by delta z, just like the left hand side, and shrink the volume to a point, and we got the body force per unit volume the right hand side. So, this is a summary of a quick recap of what we had done earlier. Okay. Of course, every lecture we have been telling left hand side, right hand side, left hand side, right hand side. So, I thought it is good to review what we have done a few classes. Of course, I think we have done several classes earlier. So, good to review this. Okay. So, now what we are going to discuss are new to the linear momentum balance. We are going to complete the right hand side or find expressions for right hand side and complete the linear momentum balance. Okay. Now, the surface forces on the right hand side for the case of fluids are due to pressure and due to viscous stresses. First, we will explain the surface forces due to pressure, because it is little simpler to understand. First observation from this slide is, and the most important observation is that the left hand side shows a stress element, the right hand side figure shows a control volume. Okay. How do you usually distinguish and what are the differences? Okay. We have discussed stress element in previous classes, more with solids and of course with fluids as well. We discussed control volume several times. Okay. How do you distinguish? Stress element, as I told you, is just a representation of the state of stress. In this particular case, it just tells about the pressure forces acting alone. Okay. On the right, and then so each though it is shown as a cube, you have a right hand side face, and then the left hand side face is not physically away, it is just opposite side of the same face. So, so stress element is a pictorial representation of state of stress. So, right hand side you have a face which is whose normal is along the positive x axis, you have a negative face whose normal is along negative x axis, but that face is just this face and then opposite side of the same face, it is not physically separate though it is shown. We also discussed that for in this case we are representing the case of hydrostatic stress. We have discussed that for the hydrostatic condition the stress tensor is diagonal, and we have only the diagonal elements, and those diagonal elements are the pressure, and because it is pressure it is negative. So, we have all the elements as minus p and minus p. Our stress element should represent this hydrostatic stress tensor. Let us see how do we do that. Now, we use our usual sign convention. If it is positive, then on a face whose normal is along the positive x axis, force should be along positive x axis. But now what you have is, because pressure is compressive, you have minus p. So, on a positive face I have shown arrow towards the negative x axis, and then on the left side face whose normal is along negative x axis I have shown pressure towards positive x axis, because we are representing minus p. Once again want to emphasize that both this p on the right hand side and p on the left hand side are representing the same information. Just imagine this face and opposites of the same face, very thin face, and we already proved that if you have an interface, a normal stress acting on opposite side of the face are equal and opposite. That is why we are representing p in this way, and on the other side we are representing p in this direction. So, it is not a physical volume, just representation. Just analogously we can extend for other directions. For example, this is a positive y face and force is along the negative y axis, and this is a negative y face, force along positive y axis. Okay, in this case this is a positive z face, p is along negative z axis, and the rear face it is a negative z face and force is along positive z axis. Now, let us come to the control volume. Look at the way on the control volume, it is also a cuboid like this, but now I show physical dimensions here. Physical dimensions are shown as delta x, delta y and then delta z. That quickly helps you distinguish between a stress element and a control volume. For the left hand side we said they are opposite sides of the same face, but now they are physically separated. You have x here, you have x plus delta x here. So, there is it is a physical volume inside your, let us say something, imagine a small control volume inside your equipment, that is what is represented on the right hand side. Now, we will have to carry whatever we discussed was stress element to the control volume, taking into account spatial variation, that is all you are going to do. And now, because we are writing the momentum balance for the x direction, on the right hand side of the control volume I have shown only forces due to pressure acting along the x faces. Okay. Now, let us take the right side face, and the direction of force is along the negative x axis as we have discussed for stress element, and on the left face the direction of force is along the positive x axis. But what is the difference here? It is represented along with the spatial location. We know that this face is at x, the right hand side face is at x plus delta x. So, here when I write this expression, it is pressure evaluated at x plus delta x, of course multiply by area, this is delta y delta z. On the left hand side it is pressure evaluated at x multiply by the area delta y delta z. So, it clearly distinguish what a, how do you represent stress element. We are representing in both phases using P, but on the right hand side in a control volume we account for the difference in the spatial location, one is at x, one is at x plus delta x, and so we have same sign convention. Remember the same sign convention is used, but taking into account the variation of pressure with spatial location. Okay, that is the difference. Okay. Now, if you understood this, it becomes easier to understand the next slide for forces due to viscous stresses. Okay. Okay. Before that, I like to recall these stress elements which I have come across at different parts of the earlier lectures. Okay. First, all these are stress elements. We have come across 2 times earlier, we are going to come across third time now in the next slide in detail. Now, the first time when we came across, we represented the stress in a solid. Okay. So, this representation, so this represents state of stress inside a solid body, and we represented the 9 components and similarly another 9 components of the stress tensor in a solid. Now, later on when we came to fluids, we once again represent the stress element. This represents state of stress in a flowing fluid, and hence we used this to represent the total stress. That is why our nomenclature became capital Txx, Tyy, Tx, capital Txy, etc. Left hand side stress element for solids representing the stress tau. The second middle figure represents total stress tensor in a fluid, and hence we represented using capital T as a nomenclature. Now, we have discussed that the total stress tensor has 2 components, the hydrostatic component and the viscous stress component. We already represented the hydrostatic component in terms of a stress element in the previous slide. Now, the next slide we are going to discuss about the viscous stress alone. So, the right side figure now has only tau xx, tau xy, tau yy. Now, why is it having only tau xx, tau yy? What does it represent? Now, these tau xx etc. represent viscous stress components in a fluid. So, this stress element represents the 9 components of the viscous stress tensor. What does this represent? This stress element left hand side represents the 9 components of the stress tensor in a solid. So, you have moved from the stress tensor in a solid to total stress tensor in a fluid, because we have already discussed the hydrostatic stress in the previous slide. We are going to discuss only the viscous stress tensor in the next slide. So, in the next slide you will see only this figure. You should not confuse this with what we have discussed earlier for solids and also for fluids. Okay. So, let us proceed further. Taking this as stress element, you should know that the 9 components represented shown there represent the elements of the viscous stress tensor for the case of fluids, which represent the stress because of the flow. Okay. This represents the stress because of under static condition. Okay. Let us proceed further. Okay. Just like we have discussed for pressure, this slide also shows you a stress element on the left hand side and a control volume on the right hand side. Of course, this looks little complicated, that is why we discussed first for the case of pressure. Now, the left hand side is as usual a stress element, no physical dimensions are there, they are just three phases let us say the right side and then the top face and then the front face, and what is shown on the left hand side, the bottom side and the rear side are just opposite side of the same faces. Okay. No they are not physically separated. Okay. And we have used the usual sign convention. On a positive phase, forces along positive direction, on a negative phase, forces along negative direction. That is why we have, for example, tau xy on this phase is along the positive y axis and this along positive z axis, but on the left hand side phase, tau xy is along negative y axis, tau xz is along negative z axis. Okay. Similarly, other components, and so this represents the viscous stress tensor in a fluid. Okay. Now, let us come to the right hand side. It is a control volume like this, and imagine a very small control volume inside a equipment. That is the imagination for the visualization for this. Now, there are several components, 9 components of the viscous stress tensor. What is that is represented on the right hand side? Because we are deriving the linear momentum balance x direction, on the right hand side only the forces acting along x direction because of viscous stress are represented. Okay. Now, let us take an example. On the right hand side phase, we have the normal viscous stress, and the left hand side also we have the normal viscous stress. Now, because it is a control volume, we also take into account the spatial location. The left hand side phase is at x, the right hand side phase is at x plus delta x. So, this normal viscous stress evaluated x plus delta x multiplied by the area, which is delta y into delta z. The left hand side same expression, but tau xx evaluated at x. So, now if you compare the stress element on the left hand side and the control volume on the right hand side, the difference, first of all, same sign convention has been used, force along positive x axis on the right phase, force along negative x axis in the left hand side phase. What is the difference? As we have done for pressure, we have taken into account the spatial variation of the normal stress. Now, let us go to the top and bottom phase. On the for the top phase, we are considering the viscous shear stress acting in the x direction. So, what is it you have considered? You have a stress vector here, viscous stress vector, 3 components are there. We are considering this shear stress component, and on the negative y phase, we are considering this shear stress component. Now, that is what is shown here. On the top phase, we have tau yx, and because it is a positive phase, force is along positive x axis, and in the negative y phase, because it is a negative y phase, force is shown along the negative x axis. Now, what is the difference? In this case, they represent thus, because it is stress element, both are shown as tau yx. So, the imagination is that you have a, okay, if I take the same plane, top and bottom, they are not physically separated, opposite sides of the same phase. So, we have seen that on a phase, opposite side of the same phase, the shear stresses are equal and opposite. That is what this represents. On the right hand side, of physical control volume, so they are separated on this phase and this phase, they are physically separated, and that is why we have y plus delta y here and y here. Of course, we are multiplying with the area, which is delta z and delta x, similarly delta z and delta x. Okay. Similarly, we can discuss the z phase as well, and what are the components to be taken here? We will have to take tau zx, that is this component, and then we will have to take this component here. and on the front face, because it is a positive face, the force is along the positive x axis, that is why it is along a positive x axis. On the rear face it is a negative z face, so force is along the negative x axis, and that is why we have force along the negative x axis. And as we have discussed for other directions, they are spatially separated. In the left hand side figure they are opposites of the same face, right hand side figure z and then z plus delta z, and that is why we have here z plus delta z here for the front face and z for the rear face. Okay. Like to also mention that when you look at books, you should be able to distinguish between a stress element and a control volume. Most of the books show straight away control volume, okay, and few books discuss about stress element. Because we have discussed more rigorously, we went to solid mechanics, understood how to represent stress, came to fluid mechanics, understood how to represent stress. We are clearly distinguishing between stress element, how to carry over that information from stress element to a control volume, accounting for spatial variation. Okay. That way it becomes very, you can clearly understand why these arrow marks are drawn in a particular direction, for example normal stresses, shear stress, etc. Okay. So, of course tau xx represents the normal stresses with spatial variation, and tau yx represents the one shear stress, and tau zx represents the other shear stress. Okay. So, all forces are shown acting along the x axis and on 3 different planes. Okay. So, let us put together what I discussed in the previous 2 slides. Now, both are control volumes, this represents the surface forces due to pressure, and the right hand side figure represents surface forces due to viscous stresses. So, nothing new in this slide, whatever I discussed in the previous slides have been just put together, because we have to account for the surface forces on the right hand side due to pressure and viscous stresses. Okay. Now, we are ready to complete the linear momentum balance. Okay, let us do that. First we will write the right hand side. We know the forces are split into body forces and surface forces on the right hand side. Surface forces are due to pressure and due to viscous stresses, and now let us write down expression. Okay. Net surface force in the x direction due to pressure. Okay. How do you write? Take this control volume, okay, and Px, P evaluated at x multiplied by area is a positive force because it is active along positive x axis, and right hand side the force is along negative x axis. So, we have minus P here, and now P evaluated x plus delta x multiplied by delta y delta z. So, that is why it says net surface force, this is along positive x axis, this term is along negative x axis, that is why we say net surface force in the x direction due to pressure. Now, let us write down expression for the net surface force once again in the x direction due to viscous stresses, the normal and shear stresses. Now, let us write down first for the normal stress. We have tau xx x plus delta x, which is along the positive x axis. So, it is positive here, of course multiplied by the area delta by delta z. Now, on the opposite side, you have the normal stress acting along the negative x axis, and that is why we have a negative sign here, and tau xx evaluated x multiplied by the area. So, this accounts for the net surface force in the x direction due to normal stresses alone. Now, let us do it for the shear stresses also. So, you take the top face and bottom face. On the top face, shear stress is acting along the positive x axis, the bottom face the shear stress acting along the negative x axis. That is why tau yx evaluate y plus delta y, and it is positive, of course multiplied by the area delta z delta x, and then and at the bottom face acting along negative x axis, so a minus sign here, tau x evaluated at y multiplied by area. And similarly in the for the other shear stress acting on the z face, okay. So if you take the front face, we have tau zx evaluate z plus delta z multiplied by delta x delta y, force is along the positive x axis, that is why this is positive here, and then on the rear face we have tau zx evaluated at z and it is acting along the negative x axis, that is why a negative sign here and multiplied by the area delta x delta y. Okay. What you should note clearly here is these expressions we have, for example, if you take the normal stress, it is at x plus delta x minus at x, because on the face on the positive x face it was along the positive x axis, negative x face it was along the negative x axis, that is why it is x plus delta x and minus x, tau xx at x plus delta x minus tau xx at x. If you look at pressure, because it is compressive and because it is on the positive phase along acting along negative direction, you have minus sign associated with the pressure at x plus delta x. So it is opposite to what we have here, and of course pressure at the x face is along the positive axis, and that is why we have P evaluated x and that has a positive sign associated with that. Okay. So now we have written down expression in one way. We can say that all these several lectures can be summarized in this one slide. To write down these expressions only, we have discussed went to solid mechanics, discussed about surface forces, stress vector, stress tensor, came to fluid mechanics, etc. So that we can write these expressions clearly for the surface force on the right hand side due to pressure and viscous stresses.